So thanks everyone for coming. I think we should start because this presentation is pretty packed. I cut off a bunch of slides, but it's still a ton of material. So my name is Matthew Tovbin. I work on Salesforce Einstein. And today I'm going to talk about TransmogrifAI. This is the library that we've built to provide automated machine learning for Salesforce platform. So first things first, this is a forward-looking statement. I will simplify it for you. Some things in this presentation have some futuristic view. So don't base your product decisions solely on what I present, and take it with a grain of salt. So let's move on. So I would like to start with a little analogy from one of my favorite documentaries. It's called Powers of 10, and it's a brief travel through the scale of our universe that starts at our own normal world, and then it zooms out to the observable universe, and then jumps back into the level of quark. So this is amazing in several ways. One thing is it just totally blew my mind to see how much complexity and vastness we have in our whole world. But another thing is that it actually gives a great analogy with machine learning. So when you start building machine learning application, this is pretty much the scale, and this is by all means not an exhaustive list. This is the scale of things you have to be taken care of. And on each level, you have a ton of complexity, ton of difficulties and uncertainties that you have to take care of. Starting from collecting your data, gathering it, keeping track of what changes and what records were modified, engineering your features for machine learning, basically picking up which values and which fields are important for your models, sampling your data correctly, implementing the algorithms, which we're amazing at, right? Like we're actually really good at building robust algorithms. We have to tune the parameters for those, select the best models, and then eventually show the predictions for our customers. And when we do that, our customers always come to us and say, hey, why this model gives me such a low probability or such a high probability of some event? And we have to be very clear on how we explain that. And that's where we have to build some prediction insights. And obviously metrics to make sure that our models perform great over time and we actually improving our models. So this is one aspect. Now, the thing for Salesforce is that we have a ton of clouds. And in each cloud, we have thousands of customers which have their own data. They store it in a different way. And then, well, similar but different. They have different meaning to it. And then each of those customers, they want to get some predictive capabilities for their applications. And this puts an extra challenge for us as a platform developers. How are we going to go and build machine learning applications for, let's say, American Red Cross and Fanatics? Those are completely two different data sets, or actually not two, multiple data sets, and models are very, very different. The way users interact with data is different. The patterns are different. So we obviously cannot afford to have data science teams that would sit and babysit all those little applications. We needed to make this scale and work in automatic fashion. So here's a question to you. How long do you think does it take to build a machine learning application? Like, make an intelligent guess. And this photo on the left should give you a little hint. And it's an image of a black hole. So it's actually more than months, right? So on average, actually takes a lot of time, starting from product development, data collection, so forth. So we wanted to take this time and make it into hours, so we can build prototypes of applications really, really quickly. From a customer perspective, we introduced Einstein Builder. And this is the application that actually gives the same power of machine learning to the fingers of Salesforce administrators who can go and click through the predictive application and get their predictions back to their applications right away. For me as an engineer, I was like, can we even do that? So this is like on any data, any machine learning application. Can we even do that without me being awake at 3 a.m.? That's the main question I was bothered with, by the way. So just getting the most of sleep. So is there like a formula we can use to cope with this whole complexity and diversity of data sets and machine learning applications, and actually take this time that we spend, where we go for months and months, into hours, where we can take a data set, do some magical transformation on it, and then get a prediction back. So this is like a dream, right? Sounds a bit of a, but we're on a Dreamforce, so we're allowed to dream, and actually we're big dreamers too. So we went ahead and we were crazy enough to actually try and build it. This is one of my favorite quotes. It's actually kind of should give you an idea of like how difficult it was for us to hide this whole vastness from the developer. So how can we actually build a good level of abstraction to access, to cover this complexity and actually being able to stay productive and deliver value to customers. So it boils down really to this dilemma between complexity versus abstraction. So I put some paintings here where you can, from left to right, you have from very complex, detailed images, you go to a more abstract piece of this like black quadrant of Malevich. And at some point, you kind of start losing the details, but you still can identify that this person is happy and on this Picasso painting, and he's probably in love and flying over the world and amazed with the stars. So we want to find a good level of abstraction that still allows us to operate on those concepts of like, okay, let's take those numerical features and use them, or let's take those categorical features and skip them. So we want to operate on a higher level of abstraction, but without losing too much detail. And this puts us on a journey of finding this appropriate level of abstraction. So how can we build an interface for developers that allows us to find this appropriate level of abstraction of building machine learning application? So here's some examples for you. Let's imagine language like C, right? So it's a low abstraction language, but it allows to build a vast majority of applications. The problem with it is that it's actually pretty much error-prone. You repeat yourself a lot of times, you make all the same mistakes, and then we know that actually, eventually, good libraries win. So if you have a robust library for C, it wins. And then higher abstraction languages, let's say SQL, right? SQL is extremely limited, but it's such a superior way of explaining ourselves to a machine when we want to do some ETL jobs. I don't know if there's anything more useful than SQL for working with data. There are different approaches. So far, there's nothing. So we wanted to find something like this, but for machine learning. And this is how we built TransmogrifAI. So the TransmogrifAI started as a library of a bunch of transformers. That's why we have this image here. And it eventually grew into a library for machine learning engineers to build applications on top of Spark. And we aim to achieve human-level accuracy with a 100x reduction in time. This is really powerful because we optimized on one thing that we cannot replace is our time. So as much things as we can automate, we would do that. And going back to the Grady Butch quote, right, we have the complexity part. Obviously, it's not simple. So under the hood, TransmogrifAI hides a lot of complexity of machine learning aspects from engineers. But it also gives the power for users to operate on the data types the way they see appropriate. Let me give an example here. Let's say binary type, it extends a numeric type, OP numeric. In a regular programming language, binary is just it's a separate type. You cannot operate on it as a numeric. From a machine learning perspective, it makes a lot of sense. Or treat it as a single response value and use it for binary classification problems. This is what we did. So we actually adapted the hierarchy of types to match machine learning needs. But moreover, we actually also applied it to to the Salesforce type hierarchy. So whoever is Salesforce customer will have their data jump into this and can get a machine learning app running in almost no time. Whoever is not Salesforce user, they can adapt their types to Salesforce types, which are generic enough to take care of almost any problem, as we already proved with our platform. So we took those types, and how did we use them? So you can see like a little Scala snippet here. Whoever codes Scala would can appreciate, and whoever doesn't, still, you can see all the same types here being applied on the operation. So let's say I want to tokenize some text. It's as simple as writing one line of, well, it's pretty stupid tokenization algorithm here, where I split by space. Don't do that at home. But hey, you get a text list back, and then you can operate on the text list as a bunch of words, do n-grams and so forth, and TF-IDF. So that's like a one value operation. And then you go ahead and you apply it on the whole column of your data, right? We call it a feature. Think of a tabular data, and then you pick up one column, and we call it a feature. And you can apply the same operation on the whole feature now. And then when you have enough operations where you see, OK, those features match, and then you can stitch them into the workflow where you go and materialize all your data for machine learning algorithm. Let's look on a very short example of predicting a book price. So it's a regression problem. We would like to predict the price of a book based on some dimensions such as author, title, and a description of a book. And we define those features, and then we do some feature engineering. We didn't have to, but we decided, right? Let's concatenate title and description, tokenize them, run a TF-IDF transformation, and then we run this magical thing. We call it TransmogrifAI. So this is something that we went ahead and we built. It's a method that contains state-of-the-art transformations and functionalities that we find to be very useful for all those data types that I spoke. What this does under the hood, it actually takes your data set, generates those features, and then applies the transformation in the most efficient way possible. It runs the pivot on the author column, and then applies your custom transformations that you picked. And eventually, it materializes some vectorized form for machine learning algorithms to feed from. We run cross-validation right away, run model selection, evaluate it, and eventually we spit out the best model. That's all we care about, really. Like we really don't want users to mess with the data transformations, picking up features, unless they want to, and they can, but they don't have to. They can just use the TransmogrifAI shortcut and move on. So we really focus on three main areas in TransmogrifAI. We're trying to automate feature engineering, feature selection, and model selection. So here's some examples of feature engineering. We take those types, and then we, for example, age, we automatically find the buckets that match those age features and bucketize it. So we reduce dimensionality of data, and it becomes actually a good predictive field for machine learning app. Or for emails, we check if the email is spammy or not, or pick like a top email domains. Things that most machine learning engineers would manually do, we already automated. And then we made it the way that we can go ahead and extend the library. So we borrowed Spark concept of transformer and estimator and reused them, but added some types on them. So now we could go and expand the library with more and more features. Most importantly is that we keep a ton of metadata. And this metadata helps us to build insights on the models and insights on the predictions whenever we deliver them. So we take care of those question users that go ahead and ask, like, why is this 0.6? Well, that's because, and you show them the metadata, it actually shows which fields have more or less predictive power in each particular case. We actually use this metadata also to select the features. We apply a ton of algorithms on top. So depending on each feature type, we apply different technique to make sure that we don't include bad features which decrease the performance of your models. For example, Kramer's V is one of the top techniques for categorical features. So we went ahead and implemented it. And we made it so people can, again, extend it. And we build it in a way that it stays a library. It doesn't stand in your way. So if you don't like the algorithm or technique, you can fully disable it. One of the main problems for Salesforce is the leaking features. Not much of the data sets that you play with have those problems. But in Salesforce, where you have a tabular data that is constantly modified or mutated by external processes, it's actually a big deal. So here's an example. Let's say we want to do lead scoring. Predictive lead will become an opportunity. Well, before it becomes an opportunity, a lot of times there is a estimated estimated lead price is being updated. So this field is closely correlated if this lead becomes an opportunity or not. So we obviously want to exclude it because it decreases the power of our models. And I don't want to do it myself. I want the machine to do it for me. So it's actually as easy as writing one function call. So price.sanitycheck. So this goes to example of book prediction again. Price.sanitycheck, and then you can do, OK, remove bad features, and what kind of correlation type you want to compute, and so forth. Next step is the model selection, where we go ahead and we try to optimize on all the possible models there are. Random forest, logistic regression, gradient boosted trees. We compete them, each one against another, and then we pick the best parameters. For users, again, it's very simple. They just specify the grid. They actually don't have to. They can rely on our own default grids that we granularly picked, and then they can use them. So I'm going to show a little morbid demo. It's pretty classic. It's a Titanic survival problem. Oh, I don't see this. Let's see. I'm going to end show. And I'm just going to demonstrate. Can you guys see this? Yeah, looks good. So I just want to demonstrate how I'm going to go and build a code for predicting survival on Titanic. So this is pretty much a classical binary classification problem from Kaggle, where we have a list of all the passengers of Titanic with their names and age and their onboarding station. And then we have a label for the person, did the person survive or not. So we want to identify which fields, which dimensions of the data actually influenced a survival of a person. This is pretty much the whole code you have to write. You define a Pojo class, or in Scala we call it a case class, that contains all the fields for your data. You spin up a Spark session. Well, we read some data with a simple reader. So in this case, data reader, CSV case of type passenger. We create the features. We run our magical TransmogrifAI. We don't have to, but in this case, I chose to do it. And then we run the model selection. And eventually, I just print the model summary. So I'm not going to run it, but believe me, it works. So because it takes like about a minute. So we have a handy script for Gradle to do it. And pretty much ends up like this. It will show you how many models it evaluated. So in this case, it evaluated random forest classifier and logistic regression. It shows you how many models it did. And then it's, OK, in this case, we picked up a logistic regression model. And these are the evaluated metrics for the model. And it shows the top model insights and so forth. You can also dig in and see the full model summary and see the score summary and so forth. And this library is actually very cool for exploring the data also with Databricks or Jupyter Notebooks or just Scala REPL. So you can just literally, in one line, boot up your Scala shell, Spark shell, and then do it from there. OK. So how well does it work? It works pretty well. It works so well that actually Mark himself tweeted about it. I was really proud about this tweet. So I decided to put it on the presentation. So currently, this library supports more than 3 billion predictions for Marketing Cloud and predictive fleet scoring for the Sales Cloud and the Service Cloud. We have a ton of applications already using it internally. So takeaways from you. Try to define a good level of abstraction. Use types, really. Stop using Python. And automate everything. Automate your model selection, feature selection, and like really, Scala is so cool. And you can get TransmogrifAI today by just going to this website. It's fully open source as of a month ago. And it runs on Apache Spark, so you can get a scaling part free, right? So you can play with your toy data and then run it on hundreds of nodes. If you are grateful for what you saw, go to GitHub and like star us. We've been trending on GitHub for the last month, which is really cool. What else? For further exploration, we have some talks from my colleagues in the past, so you can go check those out. And the most important slide is thank you for coming to my talk. I can answer questions. I don't think I have time. I have 30 seconds. One question. OK, no question. Awesome. Thank you for coming, folks. Thank you.